So today's lecture is about affine spaces and hyperplanes, but I will first take a few minutes to talk about what happened last time. So there was a mistake in the algorithm. Now this is not typically what you see for Newton algorithm. This is a little more advanced version of Newton algorithm that you might find in a typical optimization book. So this is an optional part of the algorithm, but it's necessary if you want to know. You will find a minimum, maximum, or it's just a saddle point. So what happened, the 2D version got mixed up with the general version. The 2D is very easy to use the determinant and the sign of the determinant to say if it's bigger than 0, that means if the eigenvalues have the same sign, both positive and negative, that can lead to minimum and maximum. And if the determinant is negative, that's the saddle point. But what happens in high-dimensional cases, because you might have odd number of eigenvalues, that's just not true. So good classification in general, just somewhat simpler, is to just say that if the gradient is 0 and the Hessian is, that's a necessary condition. Now if the Hessian is invertible, which means if the determinant of the Hessian is not 0, if all eigenvalues are strictly positive, then that's a minimum. Geometrically, you can imagine that all the local curvatures are making a bowl shape, and that forms a convex region. And that means it's a minimum. The one-dimensional case was the second derivative is positive, right? Now, if all local maximum, if all eigenvalues are strictly negative, that's a maximum. That's like a concave function. The second derivative is negative for the one-dimensional case. Now, for the case that the eigenvalues have mixed signs, this is not, we call it saddle point. It's not a good solution because it's neither a minimum nor a maximum. Another case when the determinant of the Hessian or Hessian is 0, then the test is inconclusive. So we can go back to the example, and then I modify the algorithm like this, that I take we had it last time too, I still keep the same condition. If the determinant of the Hessian, its absolute value is less than delta, that means it's almost 0, then we don't have enough information to solve the problem if you wish to solve the problem using the Newton algorithm. Of course, you can make a hybrid algorithm and then switch to gradient descent or use other techniques to continue. But if you want to continue with Newton algorithm, the Hessian is singular at this point, and we cannot continue. Next, we check if the gradient is, the norm of the gradient is 0. This is the necessary condition. Notice that if the norm of the gradient is not 0, we already checked that the Hessian is not singular, so we can just continue else, right? If the norm of the gradient is not 0, we go to else, and we already checked that the Hessian is non-singular, so we just update the solution. Now the case that the norm of the gradient is 0, less than delta, or numerical 0, then we check to see if the absolute value of the determinant of the Hessian is bigger than delta. And it must be, because previously we checked, right? At this point, this condition is always true, which you could basically drop it as well. Now we check if all signs, so I get the eigen H dot values, get the eigenvalues of matrix H in Julia. using linear algebra package. Sine takes the sine of them. The sine function gives you 1 if the sign is positive, gives you -1 if the sign is negative, and gives you 0 if the input is 0. So the output of sine is either 1, -1, and 0. Dot, because we have a vector of eigenvalues, I want the sine function to act on every entry of the vector. And Julia dot will do that for you. So I have a vector of sines of eigenvalues. At this point, again, I check each of them to see if all of them are bigger than 0, positive. All, that means if I have a vector of true, false, all converts all of them into one true, false. It's true if all of them are true. It's false if at least one of them is false. So if all of them are positive, now we know that the algorithm is converged to a local minimum. We print local minimum. Otherwise, the opposite, if all of them are negative, we know it's a maximum. Else it's a saddle point, which is not good. We don't know if it's a minimum or maximum. So that fixes the algorithm, and if you run it, you see that it will converge to a local minimum for this function as expected. And the solution is, of course, 0. I won't spend time again going over it, but that's basically the same example. Now, the second example, if you remember, there was a mixed output. We expected minimum. The algorithm was telling us this is a maximum. Because for the last notebook, I multiplied my function by negative to use the minimization of the gradient descent instead of maximization. Then I forgot to remove that negative. So whenever it was maximum, I would get minimum and vice versa. Okay, so for the second function, I now removed, there was a negative here, I removed it. So be careful, because of this negative, we would get the opposite condition. So the algorithm is exactly the same. You can define your function, and we can run this. And we find a local maximum after 8 iteration at point 4.47 and 0. Now, my initial guess was 3.5 and 0. It's roughly here. So this is a maximum. Now, if I change this to maybe 0 and say 3, now we are here and we expect to find a minimum. That's what we would expect, but this is a flat region of the function. It turns out the curvature, the eigenvalues of the Hessian is singular. That means it has at least one 0 eigenvalue. So this middle part is a tricky part, right? So for this particular function, when we are in this middle part, it's very difficult for the algorithm to move. It's a very hard example for Newton algorithm. So I changed this to maybe 3.2. Let's see if it works. Still not good. We may as well give it the solution. 3.5. It works. But this is a good example to see non-trivial if you cannot visualize your function. If you could not see that plot, it would be very difficult to find a good initialization. Random is, of course, always a choice. So in this case, it converges to local minimum. So we fixed the Newton algorithm by revising the conditions for the second derivative. Okay? And hopefully this cleans up the complication we had at the end of last lecture. Do you have any question for this? I want to switch to today's lecture. It's clear? Okay. So the updated notebook is on Canvas. I replaced the previous file, so you should have the updated notebook. And again, as a good exercise, you can combine gradient descent with Newton algorithm. Whenever the Hessian is singular, switch to gradient descent. Make a hybrid optimization for yourself. Then that should hopefully work for these cases when the Hessian is singular. Okay. So today we are going to talk about affine spaces and hyperplanes. We are focused first on a 2D case, R2. But much of the things we talk about, it generalizes in the obvious way that the dot product is, if it's true for R2, it is true for Rn as well. But next time we will generalize it to Rn and hyperspaces. Now, one reason we cover these topics is because that's how we can satisfy the condition for Rob 101 to be prerequisite for other courses, such as computer vision and machine learning. So it's important we cover these topics. Now, another reason is that, well, these are very great examples of applications of linear algebra. And that's where you feel perhaps more satisfied that why we learned all somewhat abstract concepts, and now you see them in application. So in particular, we want to focus on a simple example and see how can we separate our two plane into two halves. We want to revisit the idea of orthogonality, two vectors being orthogonal, and what it means in this case, how we define a line using the dot product. And then we want to talk about affine subspaces, or a better name is linear variety. These are parallel subspaces to the line that we see initially. We define it to go through the origin, and then we want to generalize it to any line, which might not go through the origin. These are parallel cases to the case that goes through the origin. These are called linear variety. This figure is R3, but you can imagine it conceptually for Rn. This particular figure is, of course, R3. These are planes that are intersecting. We just have a bunch of planes in 3D, and these planes intersect each other. What is interesting is that each plane is dividing the space into two subsets, two halves. each side of the plane, right, forms 1/2 of the space. But each of the plane is doing that. Then we can think about, for example, this particular region here, or this particular region that we might have here, right? These are hyperplanes in general, planes in 3D, or it could be lines in 2D, that separate this space, or we call them separating hyperplanes. This is really what is behind the linear classifiers. Yeah, you have a question? Plane is in R3. So the question is, what is the difference between plane and hyperplane? So whenever you hear hyper, this is for, you can imagine any dimension that you cannot visualize, which is bigger than R3. We call them, now what is a plane in R4? It is something, but, so let's call it hyperplane. Make our life easier. But you can call it plane in R4. So plane is specifically, if you say plane, it's understood that it's in R3, but if it's hyperplane, then it's bigger than R3. So this is the core of linear classifiers, because if you can think of your axis as, like you have here, let's say x1, x2, right? And maybe x3, because it's 3, but x3 is your, you can call it y or z. It's your output, right? If you can divide this space based on where x1 and x2 are located, then you're classifying the space. If your input is in one location, you can say, okay, this is the category it falls in based on that region. If it falls into another location, you can say that's another category. In a sense, this will give you a multi-class classifier, which is linear, okay? Or in general, in linear programming or quadratic programming that has linear constraints that we see in the next lecture, linear constraints are similar to these hyperplanes. And satisfying constraints in an optimization is equivalent of respecting these constraints and finding the region that basically is your feasible region, or it's the region that maybe if you satisfy all the constraints, this is what's left out of the space, right? That will be your feasible region. In control theory, in control engineering, which is heavily based on optimization in today's practice, quadratic programming is used heavily, and that's what they do. Maybe this is the region your system's actuators can take input. Beyond that, it's just not feasible, right? So it has both physical examples or something non-physical, maybe classifying dog and cat video on YouTube, right? It's the same problem. Equally important. Okay, so now we're going to build up gradually to that point. But today, let's see how the 2D case will work. Let's revisit dot product. It's been a while. This was in lecture 11. We defined the dot product of two vectors for vector space Rn to be the sum over multiplication of their respective entries. So if we have u and v, they're part of Rn, The dot product was basically U1 V1 plus U2 V2 plus U3 V3, like all the way to UN Vn. And that would be this sum that we see up here. UK Vk, k is from 1 to n. Now the notation was this bullet point here, dot. But I'm going to switch to the grown-up notation here from today. Now you're grown up. It's lecture 22. Mostly because I like it. Some people also write like this, but I really don't like this notation for dot product. I don't know why. We don't exactly choose what we like. This is my favorite notation, which is a standard notation as well. OK. That was the dot product. Once we have a vector space, we could define the dot product. This would add a structure to the space, which was actually equivalent of transposing the first vector and then multiplying it by the second one, which we could use matrix multiplication, right? Seeing this first row vector as just a single row matrix, we could use the standard matrix multiplication to calculate a dot product, which is just a transpose of the first vector times the second one. And this is our dot product or inner product. So inner product is more general. Dot product is an inner product, right? OK, this is just a review. What was the utility of the inner product? So inner product was useful when we wanted to talk about whether two vectors are orthogonal or not. We could talk about the angle between two vectors. This structure helps us to know when, for example, W1 and W2 are orthogonal. It means they form 90 degrees angle. So if the dot product is 0, we knew that these vectors are pointing to the direction in the space that they have nothing in common. They are orthogonal. Now, this concept is so important and common that we even use it in everyday speech, right? So what I'm saying is orthogonal to what you're saying. So that's exactly what we mean. They have nothing in common. So as a result of that, this dot product nicely captures this structure. When we calculate the inner product of W1 and W2, we get 0. And of course, it doesn't matter which way you do. Let's say W transpose times W2. We gave a simple example, right? So we have W1, W2. We can use numbers, and then if they are orthogonal, the inner product will be 0. Okay, this is just a review of dot product. Now let's see, do you have any question for dot product? Clear? Okay. So let's see how we can use this structure of dot product or inner product to define a line. Maybe you didn't think about it this way, or maybe you did. I'm guessing this is new to most of you. Now consider the set of all points in R2 in the plane such that if you take any vector A, non-zero, A is a vector in R2 and is not 0. You see I'm visualizing it here in the bottom. Imagine all the points or vectors x that the dot product with A equals 0. We can, of course, talk about A being a 2 vector, A1, A2, X again, X1, X2. These are 2D vectors. And the dot product, we know that it's just basically A1 times X1 plus A2 times X2. And now we're saying that this is 0. What are the possible values of X? What are the possibilities? So first of all, what does it mean that the inner product of A and X is 0? They're orthogonal, right? So whatever is X, whatever it might be, is orthogonal to A. Now let's imagine we are visualizing A here, an arbitrary vector that is not 0, non-zero. Now, if given this constraint, any vector that satisfies that constraint, it must lie on the line that is orthogonal to A, right? You're trying to solve for this. Okay, so yeah, you can do that. You're saying that what is the value of x1 and x2, the coordinates of x1 and x2? You can, but we can just talk about it as a set. What does it look like? The set of all of them, right? There will be any vector on this line, right? Regardless of its magnitude and regardless of its direction, the dot product will be 0. So it's going to be an infinite line, which is a line, right? So it's very interesting that pick any vector, A, non-zero. You can define a line by saying that line is a set of all points, x2 in R2, such that its inner product or dot product with A, which is a non-zero 2D vector, is 0. All the points or vectors in this set forms a line. Now you might remember A as a normal vector, because by definition, this vector is orthogonal, is normal to this line. So A is the normal vector of our line. So given a vector as a normal vector of the line, we can define the line using this constraint. Now, in addition, this line passes through the origin. It's not any line, because if the dot product is 0, x equals 0 is always an option, right? So the origin is always an option here. Maybe. So this line must pass through the origin, But depending on what is the actual direction this A is pointing, right? Because it could be like this, for example. Then the line will have different slope. It's not going to be the same line. Imagine all the possibilities you have, which is basically going around a circle, regardless of the radius of the circle, you can define a line. There are infinite possibilities. Just because A is in R2, you have infinite possibilities, any real number. So this is a line that goes through the origin. And you can talk about x1, x2, x3, just different points, right, in 2D. Probably it's better not to use this notation. What should we call them? B, C, D, different points. B has B1 and B2, okay? Now, what you're familiar with is probably this equation here. And that's a line too. It has a weakness. We're going to see what is the weakness of defining a line that way. What is the weakness of y equals mx plus b? Or it can be. Let's say b is 0. The weakness remains. No, that's okay. So it's about the slope of it, right? What if the line is vertical? What's the value of m if the line is vertical? Then m is infinity. It's not something we can work with, right? I mean, we write it this way, but it's not something that we actually use it to calculate. So this way of writing it, it has a problem that it excludes vertical lines, which are equally valid. There's nothing wrong with a line to be vertical. It's just a line in a plane. It is just this particular way of writing it makes it problematic, right? So it's the problem of this choice of coordinates or model. It's not a problem of vertical line. However, if you write it as less usual, maybe more advanced way of thinking about it as a set, it's the set of all points that satisfies this inner product constraint, orthogonal to A. If A is like this, right? By definition, all the points are forming a vertical line, so it's not a problem. So it gets rid of that problem. In that sense, it is a, you could say, superior notation because it doesn't have that problem, but it doesn't undermine the utility of that way of writing line. If it's useful and you're not going to face that problem, it is perfectly fine, okay? Now, it has a name. When you write it, when you define your line as a set, you can look into it like this, that, well, my line is A, X, the inner product is 0, right? This means that A1, X1 plus A2, X2 equals 0. Then you can solve for X2, which will give you negative of A1 divided by A2 times X1, right? This form that is the same thing as, you can define this to be m times x1, right? So m is the slope and is negative of a1 divided by a2. So in this case, then we say that a2 cannot be 0, because then we get the vertical line. But if you write it like this, it's okay if a2 is 0, because we're multiplying, we're not dividing, right? Okay, so, which by the way is, if a2 is 0, we have a1, x1 equals 0, which means x1 is 0. So vertical line that goes through the origin, or you don't need the last line maybe, because a1 can be anything, right? So all the lines that x1 is 0 is fixed. So this is called the regressor form. It has a name. You can call it a regressor form. Never thought we can talk about lines forever, right? 3 more lectures on lines until end of Rob 101. So hopefully now you're comfortable that it's the same thing, but when I write it as a set, it gets rid of that problem. But also it allows me to use this structure, the inner product, by saying the inner product of A and X equals 0. That defines the line for me, the constraint that I put in the set. Again, to just remind you of this set notation, for any reason, if somebody is not familiar or can't remember, we have a set, right? We write the set as this curly braces open, right? That's for defining the set. Then you define your elements or members, right? Then you draw a line, or you put 2 columns. You can put 2 columns instead of a line. Read this as such that. Now, anything after such that, this line, is the constraint that you want to set to eliminate some of the members. For example, when you say X belongs to R2, that means the entire R2. That's the set. But when you say such that, then you're going to say not all of them, those that satisfy this constraint. So what comes after this is the condition. Now, you can have multiple conditions, as many conditions you want. There's no limit. There's some flexibility how you write it. And then you close it, right? This is called a set notation. Okay. So we define our line using a normal vector as a set, and we see why that might be preferred over just writing y equals mx plus b. Is this a subspace? Trying to connect it to what we learned before. We could define any line that goes through the origin using this set that takes a vector, non-zero vector A, and says that the condition is that the inner product between x and a must be 0. So this is a subspace, or linear subspace, because it's a line. Why? Yeah? Yeah, so we had that. So just remind you of what was the subspace. Subspaces were closed under the linear combinations. That means if I pick 2 points on this line, right, and then calculate the linear combination of these two, I will be still on that line. And it does include the origin, 0. So that was also the condition. So this is clearly a subspace. And I'm going to review that example that we had in lecture 11. At that point, we were saying that if V is a subset of R2, it's the set of all points that lie on the line y equals mx plus b. Then we asked if, what's the condition for V having 2 coordinates, x and y. Y is mx plus b in a 2D plane. Basically x, y in R2, right? This is the same thing as writing x1, x2. When I want to make my grad student uncomfortable, I use x1, x2. Now we have 6 of them. I know internally the building of anger. I don't use x, y, z. But this is the same thing. So think about it the same way. So the condition for this to be a subspace, we go back and look at the example, was that B must be 0. Because otherwise, it does not include 0 vector. That's, at this point, it's obvious to you because you set x to be 0. If B is not 0, you get vectors 0 and b, and that's obviously not the origin, right? So B must be 0. And then the linear combination of them would be just, let's say, x1 plus x1 plus x2, or m times x1 plus x2 plus b. That would be the linear combination. Now I'm going to point out another way to think about this, to tie it back to the null space of a matrix. Now think about this A, the normal vector, just as a row matrix, single row matrix. Define A transpose to be your matrix A. Then by definition, the inner product being 0, which is AX equals 0, this is the null space of A. And we know null spaces are subspace. So the line that we define this way, which is the same as writing A transpose times X equals 0, this is actually the null space of this linear map, A transpose, small a transpose, as our matrix. Which you can imagine now, if you have multiple of them, you could stack them, right? That would create a matrix, and then you can talk about satisfying all of them at the same time and so on. But we'll leave it out for now. So a simple notion of line already is connecting us to the inner product, the null space. And what we're seeing is that the null space, the solution to this homogeneous linear equation, right? Any x that you get is orthogonal to the column span of this matrix, right? So any x is orthogonal to A. Sorry, is orthogonal to the column span of A transpose, right? This is another crazy fact. At the time, it would be very hard to maybe grasp. I don't think we spent so much time on this, and maybe it was a remark in the book. Okay. These are good initial places to start thinking about these abstract ideas from a very, very low dimensional simple example. That was just a remark. Think about it. See how far you can go in your mind and let us know on Piazza. Okay, now we want to talk about half planes. If you have a line for now, it's going through the origin. There's a normal vector here. Not that it matters, but it's defined, it's there. We can talk about the two sides of this line. Line is an infinite, right? It continues forever for each endpoint, for each side, from each side. So you can define one side of this to be this h plus, and the other side to be h negative. So each of them is called a half plane. Now, the obvious way to think about half plane is when you have your R2, and then maybe you talk about the upper half plane, right? Take the horizontal axis and then talk about the upper half plane. That's where y is positive, right? Or you can talk about the lower half plane. This is where y is negative. That's a little easy because then we have perfect alignment of, right, our half plane with our coordinate system. That's very easy for us to say y is positive now. This is a half plane. What we want to do, we want to say wherever this line is, I want to talk about its left and right side or plus negative side. For that, this inner product comes handy because now we have a metric to talk about sides. Without this inner product, the metric, we cannot talk about these sides. So if the dot product is positive, we're somewhere here. If it's negative, we're somewhere in the other half. Now, this is very important because now I can divide or classify the space into, let's say, plus and negative, right? So the set notation you can define is that all the points such that the dot product is positive or the dot product is negative. Now, why is this true? In case it bothers you that why the dot product is bigger than 0. If it doesn't bother you, we're good. If it does, maybe you can drop an idea. Why is not the other way around? Why this is not less than 0? No answer in chat. Yeah, you want to say something? Talking about angle?
I don't think it's correct, but like, it's not correct, but like, the closer they are together, like the closer the coordinates are, the larger the dot product is going to be. That doesn't make any sense because it could be orthogonal like any.
It's almost correct. It's not entirely wrong, but larger in, or no, smaller. If you change it, it's smaller in angle, right?
So, just like drawing horizontally and trying to figure out the next stuff. If you have two, just like you have two vectors in the same plane. Like let's say you have two vectors, you have A and X that are both pointing towards quadrant in quadrant 2 or quadrant 4. Yeah. So right where you drew A already, you have another vector going in that direction. That direction could work too. If you have two negative coordinates that they're going to multiply together to get positive, and if you have two positive coordinates, they're going to multiply to get positive. However, on the negative side, you'll have a negative multiplied, you could have a negative multiplied by a positive, and they would be less than 0, and then they would add something else that would also be less than 0.
Okay, so you're pointing out, right, to summarize, we could divide the space to quadrant and talk about each quarter of the space. And that's true. If X is basically on this side, as opposed to Z to be on the other half plane, generally X and A they have something in common in terms of direction, right? Whereas Z and A, they are, generally speaking, are pointing to the opposite direction. At least they have components that they are pointing to the opposite direction. Now we didn't talk about the angle because we don't really need it, but the angle between two vectors is the cosine of it's the inner product divided by their norm, right? Cosine. Yeah, that's from my math teachers. You have to write it in a way nobody can read. Then that's right. If it's too simple, it's not good. You can make it even better. Lazier, cosine. Okay. Because we want to record the lectures and keep it useful. The cosine of the angle between two vectors is defined that way, meaning that we can talk about the angle, right? If the angle is between 0 and 90, because the cosine is between -1 and 1, right? However, if the numerator is positive, the angle is between 0 and 90 degrees, right? That's just how the cosine function works, right? The numerator, I don't want to dive in too much, but if the numerator is positive, the cosine, the angle theta will be between 0 and 90. So then we know that x has a component that points towards A, although it might be almost orthogonal to it, right? However, if the inner product is negative, then we know that the angle is bigger than 90 degrees. It's between 90 degrees and 180. And that's how we know that's the other side. So it is from a simple, or not so simple, geometry that comes with these vector spaces. And again, the dot product, the inner product enables us to talk about the angle between two vectors. You will be very surprised to know that just recently, this was used to generalize the ReLU activation function, the rectified linear unit, in neural networks, which is a simple function. It's telling you, take a max of 0 and your signal. It is 0, right? And when it's positive, just pass whatever signal is. Right? Y equals x. This was for a scalar. Using this notion of the dot product, took such a long time, now it's a vector ReLU. So now you can have a vectorized version of that in neural networks. It's exactly using this idea. Now it's saying that instead of max, remove the part that is opposing and then keep the part that basically is left for the orthogonal part, right? Maybe this motivates you to read this on your own. Okay, so this follows from the angle between two vectors. It's not arbitrary. It just follows from the definition of the inner product. So we have successfully divided the space into two half planes. Let's talk about general lines, because not all lines go through the origin, but I want to formalize it so it will be valid when next time we talk about it as well. First, let's talk about the translation of a set. If S is any set in Rn and set of points with whatever constraints, if you have another point or vector in Rn, you can translate your set using this notation. You can write a vector plus the set. Now, this might be odd because X is a vector, S is a set. However, it is defined in a way that every element of that set will be translated by that vector. That means we add them up. So the translated version of that set is adding xc to every element of Sx here. So the addition makes sense because both are in the same vector space, Rn. And it follows from the properties of vector spaces. So this is just a notation, right? The vector plus a set means we add that to every element of that set. Now we can talk about linear varieties or affine subspaces. It's an odd name, affine subspaces, because If it's not going through the origin, then it's not subspace. But it means that it's parallel to the original subspace that was going through the origin. So if red line here is my original subspace, right? Its linear variety, or its affine subspace, is another set such that I translate my line using a vector xc. So I take my line and I translate it by a vector xc. That'll give me another line such as m. Now m is shifted. It's not you can think about this as xc. Or here, right? Now, what's the catch? The catch is that the dot product is a little more strange. Instead of talking about the dot product of a and x, now I'm talking about dot product of a and x minus xc. This defines the other lines, like blue, green. And based on the value of xc, it can be any of them in the plane, right? Infinite number of lines. So using this m, linear variety, basically we can define any line in R2. It covers the entire set of lines. Now the reason it's like that, because if, let's say I have my normal, I have my vector x, and I have a, right? This vector here, so not a very pretty picture, but this vector, black vector here is x minus xc, right? So I need to talk about x minus xc because that's the vector that is pointing along my line. Therefore, a inner product of a and x minus xc must be 0, okay? In the notes from last year on Canvas, I'm talking about points. And you can do both. If you think about xc and x as vector, then this makes sense. If you think about it as points, still makes sense. X minus xc will be the vector along the line. So, what is the inner product of a and a minus xc? It's just the A transpose times their difference. You can move distribute A transpose to this difference, which will be A transpose times x. You can move A transpose xc to the other side, and the outcome of A transpose xc will be just some scalar d, because xc is a particular vector that we translate the line, and A is also a particular vector. So we know them, they're numeric vectors. The dot product of two numeric vectors will be just a vector d. Next time we will see that this d is the distance from the origin, when we talk about the distance of a point from a hyperplane. Hyperplanes in R2 are these lines. In R3, there will be planes, and then we will generalize it to any dimension. You can write this in the regressor form, which we know that A transpose A is x1 times A1 times x1 plus A2 times x2 equals d. The regressor form, which is a familiar form of mx1 plus b, has this extra term here now, which is a general form of a line. So the linear variety of the lines that we define initially, that has this y-intercept. These are not subspaces, we know already, but they're called affine subspaces. So whenever you hear affine, there's this translation part, right? This map y equals ax. This is a linear map. A can be a map from R, let's say M to Rn. A is M by N, N by M. This is linear. However, if you write y equals ax plus this xc, this is affine. So if you really want to be precise in your language, you shouldn't call this linear, although we do. I suspect this comes from the fact that this is a line. It is linear in the sense that it's a line. But strictly speaking, mathematically, this is an affine map. The linear map does not have this translation part. Okay, so now we can talk about separating the planes using an arbitrary line, because our line can be defined using that inner product, which was important to divide the space into two half planes. So I can divide now R2 into the blue and, let's say, brown, orange, whatever color it is. And this works for any line. So these lines are not going through the origin. Origin is here. Okay? Now, this is essentially a linear classifier. This is called a linear binary classification. If I give you a set of points and I ask you to separate them into two categories using a line, this is the simplest classification problem. However, your challenge will be that you will have some examples, right, of, let's say you will have some examples of these cross, 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 and maybe circles, right? Then your challenge will be to find this A and XC. What is the normal vector here, the parameters A and XC, that will give you a line, right, that best describes this? Because you wouldn't know. You just have some examples. So the classification is actually the part that we want to solve for these parameters. And it really follows from this setup that we have. The math follows from linear algebra. Then we put it in an optimization problem to find the parameters, and then we call it a classifier. And I will make it nonlinear. Maybe next Wednesday, I'll explain how you can separate categories that you cannot separate them with lines. That's the very powerful technique that it was the big thing before neural networks becomes this popular using kernel methods. Which is still, I believe, if you take machine learning course, it's about that because that has a very rich theoretical foundation. So this sums up necessary background to know how we can construct a really simple classifier. And that follows from talking about lines, or in general, we will generalize it to hyperplanes. And for the next time, I'm going to talk about hyperplanes. Then I'm going to talk about distance, the notion of distance to the line or plane or hyperplane. Then hopefully I will introduce quadratic programming to you. This is what we learn. We construct our program, and then we use a solver to solve that. And that will lead to the maximum margin classification. You can take a look at chapter 13, but I think there are a lot of content there, but you can read it as much as you like. But I will cover what's necessary for you in the lecture. So this is the lecture for today. Let's see. We have plenty of time if you have questions. This time, next time, anything I can answer. By the way, there is, like, as mentioned in chat, there is no homework in these materials that we're covering now. These are just really, really useful things to learn. And you will see them in practice, in research, and in practical problems. So hopefully, you will be interested to learn them, although we don't give you homeworks. This is not how Google classifies a spam and non-spam. If you use a line, that's how you get all the spams in your inbox. It's much more advanced at this point, but I think that's how it started. That's the idea. All right, so this was fun. We'll have more fun next time. Have a good break and Thanksgiving. I'll see you next week.